All right, this is section 9.7 on probability. Just wanted to show you guys. I think for the most part this should be pretty easy, but there's a couple advanced problems in here that I do want to do just so you guys understand how to do them. For the most part, remember the probability of an event happening is simply on top is the what we want, and on the bottom is the total. And it's really that simple. So if you just kind of understand is what do I want to happen, that's what goes on top. And on the bottom is all the total things that could happen. And that should make it pretty easy. I'm assuming you guys are going to be okay with most of the basic probability. Here's a little bit of a weirder one, not that hard, but I just want to show you how to do this problem. So in a state lottery, a player chooses 6 different numbers from 1 to 41. If these 6 numbers match the 6 numbers, sorry for the typo, match the 6 numbers drawn in any order by the lottery, well, a lot of typos there, sorry, by the lottery commission, the player wins. What's the probability of winning? So you first got to think about, the probability that I win. Well, first off, how many total combinations are there? Well, I could choose 6 of any 41 numbers, and it says in any order, so order doesn't matter. So that would be 41 numbers, choose 6 of them. So if you use your calculator, 41 choose 6 is a huge number. It's, let me write down here, 4496388. So those are all the different numbers that you could choose. With 41, you're choosing 6 of them. Again, combination because it says in any order. Now, on any given night, only one of those numbers is drawn. So boom, there's the probability of you winning right there. Very, very, very rare. So that's again the idea of just thinking about the bottom is total and the top is what you want to happen. Now here's a really good problem. This is what I consider an advanced problem that I would hope you'd be able to do for the test. A class is given a list. Gosh, another typo. I'm really sorry about this, guys. Class is given a list of 20 problems, from which 10 will be on an upcoming test. So 10 of those 20 problems your teacher is telling you will be on the upcoming test. A student knows how to solve 15 of the problems. Find the probabilities that. Excuse me. So we know how to solve 15 of the 20. So the first question is, what's the probability that we get all 20 questions on the test right? Well, again, on the bottom has to be the total options. So how many different total combinations of questions could the teacher put on the test? Well, that would be 20 questions that she has to choose from. Here's the 20 questions that they gave you, and their teacher's going to choose 10 of them to be on the test. Now, the order that they put them doesn't matter. You know what I mean? That's why one question is going to be number 1, number 2, and so forth, but if they could switch around the problems and it wouldn't be a different test, is my point. So 20 choose 10. So 20 choose 10 is a huge number. Well, not huge, but pretty big. 184,000, 756. So really big number here. A lot of options. Now, what do you want to happen? Well, you want, of the 15 that you want 10 of them to be picked, right? Because you know how to do 15 of them. Of those 15, you want to choose 10 of them. You don't want to choose the 5 you don't know. So it'd be 15, choose 10. Because of the 15 problems you hope that 10 of them are selected. Because if 10 of those problems are selected, you're going to know how to do it. So 15, choose 10 is 3003. And right there's your answer. Now you can reduce that. So 3003 divided by 184,756 does reduce to 21 out of 1,292. So again, on the bottom, 20 questions, teacher's picking 10 of them. That's how many options for the test. You just hope that of the 15 10 are picked. All right, the student gets exactly 8 questions right. Well, once again on the bottom is the total questions that the teacher asked. That'd be 20, choose 10. There's still 10 questions on the test, and the teacher's choosing them from 20. So that doesn't change at all. 184,756. Now, we want to get exactly 8 of the questions right. Okay, exactly 8 of the questions right. Well, that means of the 15 I know, I want to choose 8 of them. That way I know those 8. But what about the other 2 questions on the test? So of the other questions on the test, right? Of the 5 questions I don't know, I'm going to have to choose 2 of those. So let me explain this one more time. I want to get 8 questions right, which means I'm going to get 2 wrong. So of the 15 questions I know, I want to choose 8 of them because then I'll get it right. Which 8? Doesn't matter. Of the 5 I don't know, I'm going to need 2 of those. Which 2? Doesn't matter. That way I get 2 wrong because I'm going to get 8 right. So I have 15, choose. Typed it in wrong. 15, choose 8 is 6,435 times 5, choose 2, which is 20. So multiply those together, 6,435 times 20. Divide it by the 184,756, and you should get your answer of, let's see here. Wait a minute. I think I did one of those wrong. 5, choose 2 of them. 5 choose 2 is 10. Sorry, I messed up. 5 choose 2 is 10. So you get 225. This is after you reduce, of course. I typed it in, reduced it. Out of, let me figure this out, 225 out of 646. And again, I multiplied the top and then divided and then just reduced and changed it to a fraction. So again, 15 questions. I want 8 of them that I know to be picked. Of the 5 I don't know, I need 2 of those. Okay, the student gets at least 9 right. 9 right means 9 right or all 10 right. Now, the good thing is we already figured out the probability to get all 10 right. That would be 21 out of 1292. So all I already figured that out. I have to add that to the probability of getting 9 right because it's one or the other. I'm going to get 9 or 10. So 9 right would be, let's see here, of the 15 I know, I want to choose 9 of them. Of the 5 I don't know, I'm going to choose 1 of them because I want 9 right, 1 wrong in this scenario. On the bottom would be the 20, choose 10. So 15, choose 9 is 5,005 times 5, choose 1 is 5. So I got 5,005 times 5 divided by 184,756, and that reduces to 175 out of 1292. So again, let me just backtrack, make sure you understand what I did. I have 15 questions I know. I want to get 9 of them because I'm going to get those 9 right. Of the 5 I don't know, I'm going to have to choose 1 of them to get wrong. Doesn't matter which one. Out of my total options. So that's the 175 out of 1292 reduce. Add those together, and I get 196 out of 1292. And that could probably be reduced as well. And I believe that gives us a final answer of 49 out of 323. So anyway, hopefully that makes sense. Now, to me, that's an advanced probability issue. It's not that difficult, and it incorporates everything we learned in the previous unit. So that's, to me, is a pretty good problem. I really like that one. All right, so let's move on and briefly talk about mutually exclusive. If you read the notes, it does talk about mutually exclusive. Mutually exclusive is simply 2 events that cannot occur at the same time. That's mutually exclusive. 2 events that cannot occur at the same time. So let's think of some examples here. For example, getting a red card and getting a black card. So you're pulling cards out of a deck and you're going to get a red card and a black card. Those are mutually exclusive. It cannot happen. You cannot get a red card and a black card at the same time. So not mutually exclusive means there's overlap. So not mutually exclusive means there must be some overlap right here. There must be something that they share. For example, aces and red card. Right over here is aces and here is red card. Okay, so there's a lot of red cards. There's 4 aces, but 2 of which are both aces and red. So that would be your overlap right there. The overlap would be the 2 cards that are both aces and red. Your overlap. That's not mutually exclusive. Now, there is a formula for probability, and it says that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now, this formula is used if you're not mutually exclusive. If you're not mutually exclusive, there is no and, there is no overlap, so you don't have to worry about it. So that's why this formula is kind of universal. You can almost always use it and it will always work. So let me just do a quick example with you. If I said find the probability that you get a red card or an ace. Okay, so let's just think about getting a red card. How many cards are red? Well, 26 of the 52 cards are red. So think about counting up all those red cards. How many cards are aces? Well, there are 4 out of 52 cards that are aces. Now here's the issue. The aces that are red, the ace of diamonds, the ace of hearts, were counted twice. They were counted right here because they were red. They were counted right here because they were aces. I don't want them to count twice. I want them to count. Don't get me wrong. I just don't want them to count twice. So I need to subtract away the 2 cards that are both red and an ace. So 2 out of 52 cards that are red and an ace. So it'd be 26 plus 4 minus 2. 28 out of 52 would be the probability of me pulling out a red card or a face card. It's the idea that if there's overlap, if the 2 things that you're talking about, red and ace, could happen at the same time, that needs to be subtracted away. Not because you don't want it to count, but because you don't want it to count twice. Now, here's a little nice self-made problem I did here that I kind of like. Let's say that we have at a zoo, we have 90 monkeys. We have some spider monkeys and some orangutans. I don't think I spelled orangutan, by the way, correctly. Anyway, and we also have some females and some males. So I made a little chart here to demonstrate the different types of monkeys we have. So some simple questions I could ask are, what's the probability that you randomly pull out of one of these monkeys? You had a list of all these 90 monkeys, and you randomly get a male. Well, that would be male with probability of a male would be 45 out of 90. Very, very simple. And what's the probability you randomly pull out a spider monkey? Okay, so we got all these monkeys, spider monkey. Well, that would be 33 out of 90. Very, very simple. How about the probability that you get a male or a spider monkey? Okay, well, let's use the formula. Male, well, how many males are there? 45 of these monkeys are males. Or spider monkeys, 33 of these monkeys are spider monkeys. But wait a minute. These 15 monkeys right here were overlapped. These 15 monkeys were counted right here because they were males. They were included in the 45 males. But they were also included right here in the fact that they're spider monkeys. So those 15 monkeys got counted twice. So we don't want that overlap to be counted twice. So we subtract away the 15 out of 90 monkeys that are both male and spider. It's not that we don't want them to count, we just don't want them to count twice. So it'd be 45 plus 33 minus 15. And we get 63 out of 90. Okay? So hopefully that problem makes a lot of sense. It really should. I could ask you a question like, what's another one I could ask you is an and, right? Let me choose a different color here just so you have a different color. What's the probability that you get a male and an orangutan? I shouldn't have chosen orangutan because I can't spell it, so I'm just kind of scribbling there. Well, how many monkeys are male and orangutan? Oh, that's easy. 30. 30 monkeys are male and orangutan. That wasn't very difficult. For me to get a male and an orangutan, it's got to be one of the 30 monkeys that's a male and orangutan out of 30. I mean, that should be fairly simple. So hopefully that type of problem makes sense to you guys. All right, next thing here is independent events. When we multiply, we like to think that the probability of A and B is equal to the probability of A times the probability of B. Now, this is only true if they're independent. I'm so sorry. So now, this is only true if once A occurs, B is not affected. If the two events are not independent, then this formula doesn't work. And I'm going to be honest with you, this formula doesn't work more times than it does because very few things are independent. So you have to make sure you're independent. But here's my point. If you're not independent, we talked about that jar problem where you pull out a yellow marble and you throw it away so now there's one less marble. That's not independent because every time you reach out a marble and throw it away, you're changing the probability of what's left. But you just have to adjust for it. And I tried to choose a problem here that hopefully makes sense in this idea of adjusting for this. So on a game show, you are given 5 digits to arrange in the proper order to form the price of a car. So we're on the prices right here. We got 5 digits in front of us. And if we put them in the right order, that makes the price of the car, we win the car. So what's the probability you win? Well, for that first number, you have a 1 in 5 chance of getting it right. But now you've placed that number. So for the second number, you have a 1 in 4 chance of getting it right. For the third number, you have a 1 in 3 chance of getting it right because you've placed 2 numbers already. For the next number, you have 3 numbers already placed. That means you have a 1/2 chance left. And when there's only one remaining number, there's only one remaining number. That number has nowhere else to go. So this is the idea of multiplying, but I considered the fact that every time I reached in, I had one less number to choose from. And if you multiply this out, I believe this is 1 out of 120. So you have 1 out of 120 chance of getting that right. So anytime somebody plays that game on the Wheel of Fortune or on Price is Right, they have a 1 out of 120 chance. Now that's if it's purely random. Hopefully you'd be able to figure out, well, the car is probably not a $70,000 car, so the 7 must not go first. But anyway, that changes things as well. So what I mean by this independent, if you go back to this monkey problem I had over here, and I did male and orangutan. Notice how I just had to think about it. I just had to say, oh, there's 30 males that are orangutan, 30 out of 90. If somebody says, oh, and means multiply, I'm going to multiply. So that's male, 45 out of 90, times orangutan, 57 out of 90. Newsflash, you don't get that. It does not equal that because that's wrong because male and orangutan is not independent. They're not independent events. If you know that you have an orangutan, it might be more likely to be a male or more likely to be a female, and we don't know any of that. So you have to understand with these charts, just use your common sense. If you don't have a chart, just make sure you think, is the probability changing as I go through these events? So anyway, hopefully that was a quick review of a probability. The probability problems are really basic. Please make sure that you try to do, like I said, in the book problems 1 through 20, I believe. And really take a hard look at them. The ones after 20, make sure you can do those too. I mean, we're going to talk about those in class, but those are some good problems for you to start on as well. All right, guys, enjoy. Have a good weekend, and talk to you later.